Hello everyone. Good evening to the sorry. Hello everyone. Welcome to the third session of online video lecture on full wave rectifiers. It is the continuation of the unit 1 power supplies. We already had two sessions. The first session was on DC regulated power supply and the second session we had covered rectifiers, and in the last session, that is second session itself, we have seen the working of a half wave rectifier and various parameters of the rectifiers. Okay, in this session we will discuss the full wave rectifiers. First, let us see the full wave we are going to discuss the full wave rectifier. What do you mean by that? Then we are going to see the full wave rectifier types. In types, we again individually going to study in depth the circuit and working of center tap full wave rectifier and working of bridge type full wave rectifier. Okay, now coming to the deeper understanding of what exactly is a full wave rectifier. A full wave rectifier is a circuit which converts an AC input voltage into a pulsating DC output voltage using both the half cycles of the applied AC input voltage. Okay, hope you are able to understand this. In the sense, in the last class or last session, we had discussed a half wave rectifier. So there, if you recall, we had said that with respect to the half wave rectifier, as the name itself indicates, only half of the AC input cycle we had used and rest had blocked in that circuit due to the circuit configuration. So here in full wave rectifier, it is unlike half wave rectifiers which uses only half wave of the input AC cycle. The full wave rectifier utilizes the full one complete cycle of the AC input. Now, because of the complete utilization, that is both positive half cycle and negative half cycle utilization of the AC input with respect to the parameters which defines the rectifier quality, such as if you recall, it was the efficiency and the ripple factor parameter. Due to usage of one complete cycle of the AC input, that is utilizing both the half cycles, hence the efficiency of the rectifier in full wave rectifier is improvised, or it is been doubled with respect to the half wave rectifier. And ripple factor, which has to be very less, in half wave rectifier it was 1.21, so which is a very high amount of noise or a noise quantity or AC component available in the DC output. Hence, in full wave rectifier circuit, it's been reduced to the greater extent, that is 0.48. So ripple factor must always be less than unity. So it means less than 1, which is we can able to get that in a full wave rectifier. Okay, coming to the types of the full wave rectifiers. We basically find two types of full wave rectifiers. One is center tap full wave rectifier and the other is bridge type full wave rectifier. Okay, now we will discuss each of these rectifiers in detail along with the circuitries and a waveform. Here, as the name itself indicates, center tap full wave rectifier. It is a type of a rectifier, full wave rectifier, or we can define it is in the form of it is a single phase full wave rectifier which uses a center tap transformer. Hence, the name has given the center tap rectifier. Now, you may be getting a doubt the what is the difference between the normal transformer that we had used it for a half wave rectifier and what do you mean by center tap transformer? Okay, as we already know that what is transformer, if we just recall the previous discussions, transformer is nothing but a static electrical device which couples the energy, which transfers the energy from input to the output circuit and also isolates load from the input circuitry. Hence, transformer acts as a protective device also. There are two types of transformers, uh, normal transformers without any taps in between across the secondary and the tappings across the secondary. Tapping in the sense where all depending upon the if we want to make use of the transformer secondary as a different sources of input of a different voltage levels, then we can tap the secondary of the transformer at a desired depending upon the desired output. So for this full wave configuration we can have the normal type of a transformer as well as a center tap type of a transformer. In center tap transformer is nothing but to explain a secondary winding is tapped at the center or middle of the secondary winding, that is the midpoint of the secondary winding which acts as a reference point. Hence the voltage at A. In figure you can very clearly see the center tapped transformer structure or a construction. The primary is same as we had seen in the half wave rectifier. The secondary of the transformer we get one more one tapping between the secondary winding between the A and B. So the tapping C is provided in such a way that the input voltage what is coupled to the secondary of the transformer will get equally divided between A to B and C acts as a reference point. That is, if our input voltage is 240 AC input voltage, then after coupling to the secondary, that 240 input voltage get equally divided with the middle reference point between A to C and C to B. A to C will become 120 volt and C to B also becomes 120 volts if our input AC voltage is 240 volt. So this is how you can have more than one tapping also depending upon our requirement. But for our configuration of a full wave rectifier, one center, one middle tapping across the secondary winding of a transformer is sufficient. Okay. Now then what is a center tap full wave rectifier? As we already know that full wave rectifier is nothing but which conducts for both of the both positive and negative cycle of the AC input waveform. So hence center tap full wave also conducts for both the half cycles of a AC input voltage. Hence able to convert AC input voltage to DC output voltage for one complete cycle of a AC input. Center tap transformer, because of its center tapping, it makes use of two PN junction diodes, semiconductor PN junction diodes for its operation of conversion of AC to DC. Coming to the circuitry and its waveform, here we will discuss the operation or working of a center tap full wave transformer. As shown in figure, it is very clearly we can see that across the input we are supplying 230 volt 50 hertz sinusoidal AC input voltage, which is coupled to the tapped secondary transformer winding with a core in between, and we can see that at secondary the input voltage of a primary winding is equally divided between A to B with C as a reference point in a such a way that A to C and C to B will be having a equal voltage values with respect that when we add up the total voltage between A to C and C to B, it will give us the total input voltage of the AC uh, mains, and depending upon the windings as well it gets reduced. We can very clearly see that there are two diodes, diode D1 and D2, connected to the load in such a way that either of the cycles the current direction is maintained uniform, that is a unidirectional current flow through the load RL is maintained throughout the one complete cycle of a AC signal, irrespective of a positive and negative. There is a current flow through the load resistor RL in only one direction. It means that itself signifies that this circuit is able to convert alternating sinusoidal waveform into a unidirectional DC pulsating output voltage. Okay, now how that happens we will see. Let us consider the positive half cycle. During the positive half cycle, point A will be positive with respect to C. C will be negative. Now downwards, the C will be negative with respect to the A is positive with respect to C and B is negative with respect to C. The other side of the reference point C is positive. Positive, negative, positive, negative. When we see the total secondary winding, A will be positive and B will be negative. So now in order to consider the positive cycle of a AC input, let us consider A, D1, RL and C. A, D1, RL and C, when we apply positive input cycle, that positive will be appearing across the secondary of the winding at A. So A will be positive. Hence, as we are using PN junction semiconductor diode, positive is connected to the anode and negative is connected to the cathode. C will be negative with respect to A for the positive half cycle. Therefore, diode D gets forward biased and hence diode D will be sets into conduction mode or acts as a closed circuit, hence able to pass flow the or pass the current flow through the diode A, D1 and RL and back to the point C. This would be the direction of the current flow in a positive half cycle. So that we can see in a output waveform for the duration 0 to pi. For the duration pi to 2 pi, Then the input AC cycle is changing its polarity. At that point of time, A becomes negative with respect to C and B becomes positive with respect to C. Then what happens? A is negative, hence it is reverse biasing the diode D1 because anode is connected to negative. So therefore, during the negative peak cycle, diode D1 is reverse biased, hence acts as a open circuit. And as B is positive during the negative half cycle with respect to point C, diode D2 gets forward biased. It means positive is connected to positive of diode, anode of a diode D2 is connected to positive at B and negative is connected to the negative at C. Therefore, now the load current direction would be B, D2, RL and C. This current flow direction is for the duration pi to 2 pi. So, hence for one complete cycle, irrespective of the positive half cycle or a negative half cycle, the current flow direction for both positive and negative half cycle would be same, that is through RL. From D1 to RL and D2 to RL. So hence it is able to convert alternating sinusoidal AC input to unidirectional DC pulsating DC output. Hope you have followed the operation. Once again, I will repeat it. Full wave center tap transformer makes use of a center tapped transformer connected with the two diode configuration. The center tap means depending upon our power requirement across the secondary and configuration of the circuit to utilize the secondary energy in a better requirement for our requirement, we can tap any number of times. So here we are not tapping more than once, we are just having a single tap. That is sufficient for our full wave rectifier operation. So what does tapping means here? From wherever you are tapping, that energy between the, so here we can see the secondary winding divided into two portions. Hence the voltage, if there is no tapping, if it is a 1:1 transformer, 240 volt is directly coupled across the secondary will be 240. As we are tapping at the secondary, 240 equally will be divided into upper half and lower half, that is 120 A to C and 120 C to B. So it makes use of a two diodes, PN junction semiconductor diode, diode D1 and D2, and load RL is connected in such a way that in both the directions it maintains the uniform current flow through the load resistor. So for the positive half cycle for the duration 0 to pi, the current flow A will be positive with respect to C, and during that time B will be negative with respect to C. So therefore the input AC positive half AC cycle is applied to the A, D1, RL and C. Hence the current load current direction flow will be A, D1, RL and C. This is for positive half cycle AC input for the duration 0 to pi. Similarly, when the input waveform takes its negative transition or it is moving towards a negative peak of a AC input or second half of the AC input, what happens? The polarities across these changes in such a way that A becomes negative with respect to C and B becomes positive with respect to reference point C. Now obviously the upper diode D1 due to A negative gets reverse biased, hence acts as a open circuit, open switch. So as the B point is positive with respect to C, that is diode D2 is, anode of diode D2 is forward biased with respect to point B positive. So therefore the current flow direction, load current flow direction would be B D2 RL and C. This is how this circuit is going to convert both the positive and negative half cycles of a AC input to the unidirectional DC output voltage, maintaining the unidirectional current flow through the load resistor. Because of this, we are able to get the DC pulsating output. So hope you have followed this. Hence it is called as a center tap full wave rectifier. It makes use of a two diodes. You should keep what are all the points to remember here. Center tap full wave rectifier makes use of a center tap transformer, and it makes use of a two diodes. These are the special qualities or a special features of a circuitry for a center tap full wave rectifier. Okay, now coming to the bridge type full wave rectifier. It is a single phase full wave rectifier circuitry or a device which converts AC input to a DC output for both of the uh, half cycles of a AC input. It means again like a center tap transformer, it also converts AC to DC for conducting for both the half cycle of a AC input. It makes use of four semiconductor diodes connected in a bridge configuration. The only difference to the center tap to bridge is bridge makes use of normal transformer, but the difference with respect to center tap is it makes use of a four semi PN junction semiconductor diodes connected in the form of a bridge, whereas the full wave center tap makes use of only two diodes, but the difference is it makes use of a center tapped transformer. Okay, as the center tapped transformer is expensive because it has to make a secondary winding tapping, so that design is a bit complex and take time consuming, because the designer has to designer will take a bit longer time rather than normal manufacturing the normal transformers. Hence it is bit expensive. That's why bridge rectifier is developed, which is going to give the same efficiency, same ripple factor as the center tap full wave rectifier is going to give, because again it's going to make use of both the half cycles of a input waveform. Now coming to the uh, deeper understanding of the operation of the full wave bridge type rectifier. Figure shows the circuit diagram with the waveforms. Here we can see that this type of full wave rectifier is making use of normal transformer circuit with the difference is it is making use of four PN junction diodes D1, D2, D3 and D4 connected between the points A, B, C, D in such a way that every direction it maintains the uniform current flow through the load resistor, hence able to convert alternating sinusoidal AC input voltage into the unidirectional DC output voltage. So same thing you have to remember, same points you have to recall. While explaining the circuit diagram, you have to explain the AC line voltage specifications, what is transformer, then you have to define what is a full wave rectifier, then what is the bridge type rectifier. So yes, how the flow goes. AC, this circuit utilizes 230 volt 50 hertz AC input voltage, which is coupled to the transformer. Transformer is again nothing but a static electrical device which transfers energy from input to the output device, providing a protection to the load circuit from the input circuitry. Here we can see the secondary is stepped down so that we can get a desired lower value of a DC output for our desired applications as a DC power source. Here it is making use of a 4 PN junction semiconductor diodes. So during the positive half cycle, that is for the duration of a 0 to pi, the S1 will be positive with respect to S2. That positive voltage is applied across the diode D1 RL, then back to the D3 and back to the S2. Okay, yes, what is the load current flow direction? Here S1, as S1 is positive with respect to S2, it will forward bias the diode D1. Are you able to understand? D1 anode is positive with respect to S1. Hence current is flowing through S1 D1, as D1 is acting as a closed switch because of a getting forward biased. D1 RL flowing through RL, then back to the again it is forward biasing the diode D3. Hence D3 also acts as a closed switch and therefore it is directly allowing the current to flow through it and back to the S2. So this is how the current flow direction takes place in the positive half cycle. Now coming to the negative half cycle, that is for the duration pi to 2 pi, that is when the AC input voltage is taking a reversal in its voltage towards the negative peak of the AC input. What happens? By this time I think you have understood how exactly the transformer positive and negative cycle voltage and polarities will be appearing across the secondary of the transformer. Okay, yes, come on. S1 now during the negative half cycle will be negative with respect to S2. Therefore, what it is doing? It is reverse biasing the diode D1 and D3. Hence, it cannot allow any current path for through that direction what we had seen in the during the positive half cycle, because now S2 is positive with respect to S1. During this time, what is positive? Which is going to get forward biased among the 4 diodes? S2 is forward biasing diode D2. Just see the path how I am reading it. S2 D2. S2 positive is applied to the D2 anode. Then point A, C, B, RL back to D. It is forward biasing. Same voltage is applied to the D4 anode point. Then back to the S1. So this is how during the negative half cycle of a AC input, that is for the duration of pi to 2 pi, the current flow is taking place from S2, C, D2, B, RL, D1, A back to S1. Just if you observe the load current for both the positive half cycle and negative half cycle, the load current is passing through the point B. That is the significant point which we have to consider. So always in the both for positive half cycle and a negative half cycle, the current flow direction is passing the point B, hence through the RL. Thereby, this circuit is going to convert alternating AC input to a unidirectional DC output because of the current flow direction in the load resistor is unidirectional one. But the output converted is a not a pure DC, it is a pulsating DC. Hope you followed, but once again I repeat it for your understanding purpose. What it is having a AC input, a transformer and 4 diodes connected in bridge form or a bridge configuration connected in series with the load RL. P1, P2 acts as a primary point, primary winding, S1, S2 acts as a secondary winding. So during the positive half cycle, for the duration with respect to waveform, I am talking 0 to pi duration. Positive half cycle of a AC input voltage is coupled to the secondary winding S1 to S2 in a such a way that S1 becomes positive. S1 becomes positive with respect to S2. Therefore, it is forward biasing the diodes D1 and D3, and as we can see, the D2 and D4 diodes are facing the cathode are facing the positive of the S1. Hence, they gets reverse biased, and D1 and D3 gets forward biased. As the positive half cycle is favoring to forward bias the diode D1 and D3. Hence, tell me the load current direction now. The load current direction during the positive half cycle would be S1, A, D1, B, RL back to the point D and D3 and S2. So current path is a complete closed path from S1 to S2. During the negative half cycle of AC input voltage, what happens to S1? During the negative half cycle, S1 becomes negative and S2 becomes positive, and hence this negative with S1 negative with respect to positive reverse biases the earlier diodes D1 and D3. Now forward biases the S2 of positive forward biases the D2 and D4. Hence, can you tell me the current flow direction? Yes. The current flow direction now would be S2, C, D2, B, RL, back to D, D4, A and back to S1. Again a closed path, it is completing the closed path S2 to S1, maintaining the unidirectional load current flow through the load resistor RL. Hence, we can conclude with the point that full bridge type full wave rectifier is also conducting for both the positive and negative half cycle of a AC input or any alternating current into a unidirectional DC output voltage. So this completes the full wave bridge rectifier, as this circuit also conducting for one complete cycle of a AC input, or we can say both the positive and negative half cycle, which makes the one complete cycle. Hence, its efficiency and ripple factor parameters are greatly improved in order to get the better performance of a rectifier as a full wave rectifier. Because of this reason, its efficiency is greatly enhanced, almost double with respect to the half wave rectifier, that is 81.2. The only reason for this improved efficiency is its utilization of both the positive and negative half cycles for conduction of a DC current. Then same thing as a center tap rectifier. Center tap also it is converting alternating AC input, or it is utilizing both positive and negative half cycle for converting that into a pulsating DC output. Therefore, only center tap and bridge, it is difference between the configuration and circuit design, but both of them acts as a full wave rectifiers, and hence center tap full wave rectifier also will be having efficiency of 81.2% compared to the half wave rectifier. And because of the usage of both the cycles, the ripple factor is reduced to greater extent, that is in both the center tap and the full wave bridge type rectifiers, it would be point 0.48. So just we can imagine, just we can see that in half wave it is 1.21, and in full wave in both types it is reduced to 0.48. So just imagine the quality of a output waveform you are able to get in the full wave rectifiers, which is removing or free from the ripples to this greater extent. So hence widely full wave rectifier types are preferred in order to get the better performance in a DC regulated power supplies. Okay, hope all of you have followed today's discussion on full wave rectifiers. Just with a small recap, I want to have brief out the things we have discussed so far. We have discussed today's session full wave rectifier. Full wave rectifier is nothing but a rectifier which converts alternating AC input, which converts AC input to DC output for both the positive and negative half cycles of a AC input, unlike the half wave rectifier which converts only for a half cycle of a AC input. Because of only this reason, its efficiency is greatly improved, and ripple factor is greatly reduced. These two points complement the performance of the full wave rectifier circuit. Then we have seen the type of full wave rectifiers. What are the types? Center tap full wave rectifier and a bridge type full wave rectifier. We have seen what is center tap and why it is called center tap. We have seen that it is making use of a center tap transformer. Because of that, the name has come, and it makes use of a two diodes. So you have to keep in remember these points, because you may get a questions, just they may ask in a design how many diodes it may use, like that. So you should be able to answer that. If you understand it thoroughly, you will be definitely able to answer the any kind of questions raised in this topic. So full wave rectifier makes use of a four diodes. This is the only major difference between the center tap and full wave rectifiers. Otherwise, performance wise, all both of them produces or having the in terms of rectifier parameters, almost all parameters of both center tap and bridge will match, just only for the reason both of them uses the both the half cycles of a AC input. Okay, now moving towards the multiple choice questions discussions. Okay, first question is full wave rectifier circuit conducts for. Yes, come on. Just now we discussed whether it conducts for only half cycle of AC input, or both the cycle it utilizes, or quarter cycle, or none of the above. Yes, it conducts for both the half cycles of a AC input. The center tap rectifier utilizes how many diodes? 2, 3, 4, or only one? Yes, the answer is B. It makes use of a two diodes. Then coming to the third question, the efficiency of full wave rectifier circuit is 100%. Is it 40.6% or 50% or 100% or 81.2%? Yes, it is 81.2%. It is double that of the half wave rectifier. Okay, what is the efficiency for half wave rectifier? It is 40.6. Double of that is 81.2. Okay, coming to the fourth one. The ripple factor of a full wave rectifier is it 1.21 or 0.48 or 48 or 12.1? Yes, it is reduced to the greater extent in full wave. So the answer would be 0.48. Yes, 0.48 is the right answer. That is answer B. The ripple frequency for a full wave rectifier is, so as it is making use of both the cycles of AC input, the ripple frequency will be double the half wave rectifier. So therefore, what happens in half wave rectifier? What was the ripple frequency? As it was utilizing only the half cycle, the ripple frequency for half wave was F naught. So here it is utilizing both the cycles. Definitely the ripple frequency gets doubled. So therefore ripple frequency is doubled in case of a full wave rectifiers. Therefore the answer is 2F naught or F naught or 3F naught or 4F naught. With this discussion, that is answer is A for this. Okay. Thank you so much. I would like to mention 2 points here. In a full wave bridge rectifier, that is the ripple frequency would get doubled because of a full wave utilization of a input AC wave, and PIV parameter also gets doubled. It would be 2 Vm in case of a full wave rectifiers, because of the only reason it is making use of the complete half cycle or both the half cycles of a AC input. Okay, with this we have reached to an end of the session. Thank you for listening. Uh, this is my team. I thank to my team. Okay, thank you.